Well, thank you all for coming. I want to talk today about something that's in the quantum information literature called embezzlement of entanglement. I don't particularly love that because it doesn't really tell you what it does. And also, when you go to C-star algebras, you're talking about state embezzlement. And I don't really like crossing borders with papers and having to tell people that, well, I'm here to show people how to embezzle states. But it's really about catalytic production of well, it's really about catalytic production of entanglement, which I like better because what we'll show is that with just a little twist, it becomes Connes Embedding Probelm. So, here's where it comes from. It was from a paper of Dam and Haydon. And they asked the following thing. So you think of Alice and Bob as having, I like to think of them as their private spaces. This is the spaces they get to deal with solely. And then they have a common resource space, which is in a tensor product. So this is this bipartite setting. And Alice can deal with this stuff, and Bob can deal with this stuff. And now the question is, so there's 4 Hilbert spaces. It's a little awkward to write things down otherwise, but so this is HA, this is HRA, HRB, and HB. So Bob and Alice start in their private spaces. Everything is in the neutral state, the ground state, whatever you want to call it, E0. And then they share some entangled state. And what you'd like to know is, well, you'd like Alice to act with a unitary on her stuff, Bob to act with the unitary on his stuff. And what you'd like to have happen is, in the end, you're still in the same state here, but in their 2 private spaces, you're now in some entangled state, say the Bell state. So I'm thinking of the case where they're both 2-dimensional spaces. And the first comment is, can you do this? No. And here's the argument. The argument's pretty simple. If you take the input vector and you do its Schmidt decomposition, it'll have Schmidt coefficients. The larger Schmidt coefficient of this whole vector is just the same as the larger Schmidt coefficient of this. Call it lambda 1. But when you look at the output, the larger Schmidt coefficient will be 1 over root 2 lambda 1. And unitaries preserve Schmidt coefficients. If they preserve the bipartite structure, they have to preserve Schmidt coefficients. So this is impossible. But then what they proved is that for all epsilon, maybe I should move to colored chalk. For all epsilon bigger than 0, you can do this in such a way that you don't get psi back, but you get back a different vector. But the different vector is close to the original vector. And so what they show is for each epsilon, as epsilon shrinks, you need the dimensions of the resource space to go up. They gave lovely bounds on what the dimension of the resource space has to be in terms of epsilon, and so on. Now, this is what they called embezzlement, because if if you have outside observers trying to watch this, their measurement instruments will have some tolerance below which they can't see things. And so if you make epsilon smaller than the tolerance, you'll fool them into thinking you've catalytically produced embezzlement. And now why do we call it catalytically? Well, if you get the same vector back here, then after you've used B for whatever, you've got this vector, and you can produce a new Bell state from it by doing things all over again. So it's, usually it's very expensive and hard to produce entanglement, but if the entanglement returns, then you get to continue using it. So later works showed it's nothing special about the Bell state. For every entangled state here, you can do the same thing, and gave very sharp bounds on what the dimensions of the resource space had to be in terms of various measures of entanglement of the output. So they have very tight, it can't be any smaller than this, but here's an example where it's nearly that. So a lot of work there for all finite dimensional spaces.
So would you expect still to produce B on the nose? Or in this?
Yeah, they still are producing B on the nose, okay, but by allowing this to wiggle a little bit. They don't wiggle the B.
So how can the Schmidt rank argument doesn't?
It still works in infinite dimensions, the Schmidt rank. So even if you allowed these to be infinite dimensional spaces, and that's what interested me in the first place, because somehow here's a picture where something can happen, but it can happen nearly in finite dimensional spaces, but it still can't happen in infinite dimensional spaces.
Why, if you allow psi to change to psi epsilon, why do you not? What happens to that argument that showed it was impossible originally?
Because the Schmidt coefficients of this could be the original one. Schmidt coefficients aren't continuous with respect to norm. So I wanted to unravel, well, what does happen in the limit? And together with Richard CLeve, his student Liu, we showed the following. I'll just draw it by a picture. So here we have Alice has her private space, Bob has his private space, and they have a resource space, but not in tensor product, just a resource space. And you start with an E0, a psi, an E0, and you have your any phi you want, unit vector in HA tensor HB.
E0 and E1. Same E0 stuff.
I just want to, I'm numbering my orthonormal basis starting with 0 like they do in quantum, right? Because 2 dimensions should be E0 and E1. What's bothering you?
E0 is in HA, right?
Yeah, this is in HA, this is in HB,
Yeah.
this is in the tensor product.
Two-dimensional vector spaces, Hilbert spaces, and you always take the first basis.
We were just calling it this.
Yeah, that's just standard because they, when they talk about qubits, it's a 2-dimensional space and they always number it E0 and E1 because.
How can they both be 0?
Yeah, I understand.
Oh, yeah. Yeah, just some if you like, for me, these are always C to the NA and C to the NB. And I number the basis 0 to n-1.
You're getting into dimension B, the vector B, right? The Bell state.
Yeah, yeah.
NA and AB,
But what I'm saying is the later generalizations, this space is larger but finite dimensional, larger but finite dimensional, any vector here. But you start, and starting here is the same as saying starting with anything that's not entangled in the, and so the later work, you put the phi here, and you can still have a psi epsilon, and then they have, bounds on the dimensions of the h's, h sub r, in order to do this within epsilon, based on how entangled phi is. Okay.
When you say it's phi on these, or like phi on these two components and psi on the other one, that means if you trace out.
Yeah, if you trace out, you get, or if you're in a product with psi, so you compress to the one-dimensional space spanned by psi, then you almost have phi. But on the one-dimensional space spanned by psi epsilon, and, well, not one-dimensional, I mean, psi epsilon tensor the rest of the space. Tracing out is a good way to think of it, too, yeah. Okay, so what we showed is that, well, this is impossible in the tensor product model. You can always do it in the commuting operator model. So you have here, you have Alice has a unitary operator here. Bob has a unitary operator here. And what I really mean by this, right, is it's UA tensor, the identity on Bob's space is what this operator is. And identity on Alice's space, tensor UB, is what this operator is. And those two operators commute. So all we're giving up is that this space is not a bipartite space, and we're not doing tensor products anymore. We're just doing this kind of product. And so, and you're getting psi back exactly. So in short, this is the simplest thing I know of something that can't occur in the tensor product theory, but can occur in the commuting operator model. Catalytic production of entanglement happens in the commuting model, but not in the tensor product model. And we'll see in a while that that's got something to do with almost with quantum groups, but also with Connes embedding. So let me just dissect a little what's happening here. Right? This U sub A it's a bounded operator on, let's call it a CNA tensor HR. And so with the, which I just identify with the NA by NA matrices over the bounded operators on HR. So it's got matrix coefficients, which are operators. And the UB is some VKL, because it's in bounded operators on CNB tensor HR, where the VKLs and this commutation, when you write things in these coordinates, it's exactly that the UIJs and the VKLs all commute. Okay. So what I'd like to do is outline a little bit of the proof of how we show this. So what you do is you look at Larry Brown's non-commutative unitary algebra. So NC of n is the universal C-star algebra generated by the identity little uij's, little uij stars. I and j go from, well, I should make it 0 to n minus 1, I guess. And such that anytime you have a concrete matrix unitary like this, that's a star representation of it. So it's almost like the quantum group UN plus, except there's no condition that the stars are also unitary.
You also want the condition that the block matrix is.
Yeah, such that and now you can write that down in equations involving the uij's, but it's just, you want these are supposed to be capital U's and capital V's to be the representations of it, okay? And the theorem we proved, well, let's let the dimension of Alice's space be NA, dimension of Bob's space be NB, phi be something in the tensor product. Then let's call that picture star so I don't have to write it all out in words, right? I think everybody understands what I mean by that. So the theorem is, one, you can do star if and only if there exists a state S on the maximal C-star product such that the state applied to U I0, and let me write phi as a summation of alpha ij ei tensor ej. So again, I'm thinking of these as CNAs and CNBs. So the sum of the alpha squareds is 1. So of course, in this second one, it's convenient if I think of the generators as V's. Yeah, Vj0 is equal to alpha ij. So to prove you can do star, you have to show there exists a state that does that. And the second thing is, for all unit vectors phi, there exists a state S on the minimal tensor product and therefore you can do star. And this is also for all dimensions.
Do you not want so maximum min? So which one is stronger? Somehow it's.
Well, so if you have a state here, then by composition you get a state here. Yeah. So the way we prove 2 is we use this stuff that's in the literature about approximate embezzlement. Those each approximate embezzlement, if you do the inner product with the original psi, you don't quite get the coefficients of phi, but you get them nearly, and you can get them nearly for all epsilon. So there's a weak star limit of those. And because you're doing it in finite dimensions, it's a min tensor product, not a max. And so that's why this. So this followed from the classic literature. We later gave a proof of it independent. Basically, we gave a simpler proof of this so in the paper, so you don't have to read all the old literature.
In the finite-dimensional case, is there a difference between having HR be a tensor product, just having finite-dimensional commuting?
It's the same, yeah. You can do finite dimensional commuting. And then the same way as with the classic correlations that we've seen, how you can split things up. You can split things up here. Yeah. So anyways, this led me to believe that this max and min tensor product were the same. So I assigned my thesis student to prove that, Sam Harris. And about a week later, he came back with the following theorem. So the following are equivalent. One is that UNCN tensor min UNCM equals the max. Probably by the way I'm stating this, you can all guess what I'm going to say. So if it's true for one, it's true for all. The answer to Connes Embedding Probelm is affirmative. So then he asked me, do I really have to prove these are min and max tensor are the same? But it's it means the two pictures are very closely related. Now, let me just say a word about his proof, because later it Gao, Harris, and Younga. The first bit of this was actually in his proof. I mean, it wasn't stated in his proof, but it's what he was getting at. I always have to look to get the numbers straight. Is that if you do the D by D matrices over the full group C star algebra of FD squared, that's isomorphic to UNCD cross-producted by ZD cross-producted by ZD. And the second is that the D by D matrices over UNC of D is isomorphic to a cross product of the C-star algebra FD squared. So almost like a Takai type duality, but you have to go to matrices. And then the remarkable thing was they looked at the, so Sam had, although he didn't state this, this was what he was using. He was using that, you know, this gives you an embedding of this one into here, and this gives you an embedding the opposite way, and then lacing those embeddings back and forth is how he was able to prove these are the same as the C-star of Fn tensor Fd being isomorphic, or Fn squared Fd squared, I guess. I don't want to do that here. But the interesting thing is the maps that define these embeddings, what Gao and Younger realized is their super dense coding and quantum teleportation. So if someone asks you what is super dense coding and what is quantum teleportation, if you look in this paper, you can see, you can show them, well, it's just this, it's these two isomorphisms. And I forget which one is which. But it's, it uses Bennett's implementation of those two to define the maps that are the so one of them defines one isomorphism, the other defines the other isomorphism. Okay.
Question about the theorem. Still, I'm still confused about the order of implication somehow. Don't you?
So if you want to be able to do this, then you can prove that's exactly equivalent to there being a state on the max tensor product. And then the way you prove that you can do this is because there's a state on the minimal tensor product that has that property. And of course, that gives you a state on the maximal. So the top is an if and only if, whereas the bottom is better than you expected.
And how does the state then relate to psi? Psi that you want.
Psi will be the GNS vector of the, H sub r will be the GNS space of this state representation, and psi will be the GNS vector.
Just so I understand correctly, you can do both 1 and 2 always?
Yeah, so 2 is, for all unit vectors, there is a state. But it's even better than you needed. It's a state on the smaller tensor. So it's kind of, that was kind of the surprise. And it was the surprise that made me think, well, maybe these two are the same. But proving they're the same would have been proving Connes, and now in fact we know they're not the same. So why are they not the same? And that's what I want to go into next, and that'll involve what we call unitary correlation sets. And the reason they're not the same is because if you look at this, well, if you look at this, you see you're only asking what the state does when you fix the outer two legs. And for any two outer fixed legs, you get the states agree, but it's when you start to look at what happens for other pairs. So, it's, you know, if you have this picture when you do E0 and E0, and now you ask, well, what if I do E1 and E1, what happens? Then you're looking at the correlations between pairs of different possible legs in this. And so we want to stack all those together in something we call a unitary correlation set. And we'll see that for those, there's parallels to the whole Tsirelson theory. Okay. So
So is this feasible? That you could just use this result somehow that you have to prove that if you take not the whole round algebra, there's just the subalgebra generated by one column, something like a sphere, and then the minimal tensor product would be the same as the maximum.
Yeah, so there might be some sort of operator space or operator system tensor product that agrees on the min and the max. And that is sort of what the correlations tell you, because the correlations, when you freeze something, then the correlations you can get in one is the same as the correlations you can get in the other. But I want to present that by stacking everything together in what I call a unitary correlation. 2 is always possible.
But then, I mean, if you have a state on the minimal, larger also you have a state on the maximal. So why
No, but yes, so if you have a state on the minimal, then you do have a state on the maximal. And so hence there's a state on the maximal that does this, and that's why star holds.
Oh.
Because star holds if and only if there's a state on the maximal. But what I'm saying is it's even better than that. Okay. So is it now clear? Yeah. So leave that there. So suppose I have a Uij and a VKL, and I look at Uij tensor VK. I'm going to change notation here, or I'll So for the moment, these are just finite matrices, which I tensor product together. And then I apply them to a unit vector and inner product with the unit vector. Sorry, I've moved my things to the other side. So this gives you an x, I, k, j, l. And I want to think of that matrix X as a matrix in M, if this is NA by M NB. All right, so these are this is the IKJL coefficient. The way to think of it is in the tensor product. And then you let B sub q be the set of all x's BQ n, let me call this n and m. So there's the quantum unitary correlations are all the matrices you can get that way. Size a unit vector in yeah, I probably should have called it it's playing the role of psi. Probably should have written it as a psi. Unit vector.
The question is, do you only want finite dimensional representations or arbitrary?
Finite, where these Uijs are coming from finite dimensional matrix algebras as well. Nothing to do with the n and the m, but you know, it's a finite dimensional representation. So what I want to do is take a finite dimensional representation of UNC and a finite dimensional representation of UNM, tensor them, and then do a state, finite dimensional state, and look at all those. And then and you can all guess what that is. It's the same thing, but you do arbitrary dimension, and you demand that the UIJs commute with the VJLs. And so you have these two sets of unitary correlations.
So compared to, say, ordinary correlations, the differences you place is...
This is like the CQ, and this is like the CQC.
Yeah, but compared to the ordinary correlations you replace is like universal POVM algebra by this unitary.
By this universal, yeah, by this matrix unitary. And that's all that's going on. That's why we call them unitary correlations instead of POVM correlations. Okay? So the theorem is, well, the closure without writing it down, let me say it's B min NM. So this is the thing that comes from states on the minimal tensor product of the two. And of course, BQC is exactly the things that comes from states on the maximal tensor product. We have Slofstra's results. In fact, BQNM is not closed for all N and M. Let's make the stronger statement. That's from the Dam and Haydon picture. If it was closed, then you could do exact catalytic conversion. So if you just go back to their very first, where they're dealing with the Bell state, that shows BQ22 is not closed. Otherwise, you'd be able to perfectly embezzle the Bell state in the quantum picture. So, if we'd ever written these down, then long before we knew the CQ wasn't closed, we would have known these weren't closed. And then we have the analog of Yunga et al. Ozawa theorem that BQNM closure is the same as BQCNM for all N and M, if and only if Connes embedding is true. So it's the exact analog of, the closure of the quantum correlations are the quantum commuting, if and only if Connes embedding. So we know there exists some N and M for which these sets aren't the same. The other thing that's a little interesting is that it's a little hard to see at first, but these are balls they define norms. On the tensor product. And the two norms they define are admissible cross norms in the sense of Grothendieck. So these are so Grothendieck has this whole theory of tensor products, and there's good tensor products and there's bad tensor products. The ones he wants to study are the admissible cross norms, and these arise this way. And so it's just kind of a trivial thing from the above. If we call these, I don't know, the Q norm and the QC norm, then norms are the same if and only if their unit balls are the same, if and only if that.
So what norms if you restrict them to individual factors?
Well, if you take the norm and you fix, like say 0, 0, and you look at all the ij's, you get all unit vectors in the ordinary Hilbert space norm. So, so what these balls look like is each time you slice them by freezing, say, a K0, L0, and look at the ij's, that's the full Hilbert space unit ball. And the differences between them is, well, if I have this vector in this copy of the Hilbert space and this vector in this copy of the Hilbert space in the one ball, do I have that in the other ball? So it's when you try to look at the correlations, when you let the K and L vary between which vectors you're getting in each copy of this Hilbert space, that's the correlations that tell you whether or not the balls are the same. And since we know Connes embedding is false, we know those aren't the same.
So that's not individual factors, just the fact that it's an admissible cross norm that contains that individual factors is just all norm.
What is this?
Yeah, but the thing is, if you what does this norm look like at all? And if you look at all the, say, x, I, K0, J, L0, that are in the unit ball of, that can be realized as correlations.
I think the question is, what it's admissible for which norms from MN?
Oh. All norms are equivalents on finite dimensional spaces, so admissible is
typically is inequality with constant 1, right?
Exactly. Typically, it's just norm A tensor B equals norm A times norm B.
that's the cross norm.
Yes. So what are the norms on MN and on MM you take? So are these Hilbert-Schmidt or
It's the Hilbert-Schmidt norm. Yeah.
the kind of strange tensor product between Hilbert spaces?
It's a funny tensor product.
Very hard to compute this norm.
Sure.
Well, yeah, because if you could. Yeah. Okay. So how's my time doing? It's almost time for break. there's one more thing. Well, there's two more things I want to do. Should I break now, or each of them will take about 10 minutes. So I can do one of them and then break, or we'll just see what your patience is like.
In the story, you place this Brown algebra by the
Yeah, well, that would be interesting, right? And if how much of this goes through when you replace Brown by the unitary quantum group, and this suggests that maybe there's some connection. This suggests that there's maybe some connection to Connes embedding, possibly. The other thing that's interesting is the other thing that's somewhat interesting is, right, the unitary quantum group is a quotient of this. So you can pass here to the ZD cross ZD action, and that's MD of some quotient of C star FD, and I don't know what that is. I've never analyzed it carefully. But that might be an interesting quotient of C star FD to work with. There's
right? They wanted to prove strong embodiment for essence vector. But they have, yeah, similar sort of decomposition.
And also, we talked about it, but still quite remember exactly, but the relationship between the strict algebra of the big group and Brown algebra is also the easiest book already. You write some kind of embeddings both ways in this book of thing.
So there's a lot that has been explored and a lot that hasn't been explored. Yeah. But I think for a quantum groups crowd, it's close enough to a quantum group thing we're doing here. But okay. So the next thing I want to talk about is something we call self-embezzlement, because we really thought this was going to give us a way to prove Connes' fault. And so here's the task. What I'm going to do is I'm going to take Alice's private space, Bob's private space, their private resource space, to all be the same space. And so if you like, you can just think of this as some Cn. And I'd like to look at this task. So I want to take, I've got my 4 legs again, because I'm in the tensor model. They share some common entangled state. They act with unitaries on the tensor products. And they want to get psi back, right, the embezzlement picture. And what they'd like to embezzle, well, we know given anything, so suppose we try to embezzle the embezzlement state. Of course, we know we can't do this. We can't do this, but we know usually we can approximately do this, but the state that you need varies with what the phi is here. And so here's the, so of course you can't do this exactly. But now suppose you try to do it approximately. And the theorem, this is with Benoit Collins, the earlier suspects and myself. If the largest Schmidt coefficient of psi is smaller than 2 over root 3. So this just guarantees that psi is a little bit entangled because it doesn't have, if it wasn't entangled, the Schmidt coefficients would just be 1. So forcing some entanglement. And suppose I do have this picture. So psi is a concrete vector. I don't get to vary the dimensions in here at all, because everything is coming from the same space. But if I did have unitaries that give me psi back and some perturbed thing here, then the perturbed thing has to be far from psi. And the thing to note is that this is, these constants are independent of n. So if you try to do self-embezzlement in the tensor model, any dimension, as long as you have some bound on how entangled this is, you can't do it.
Can you do it just by the Schmidt coefficients on the left, the Schmidt coefficients on the side, and on the right, you want them to be like, I mean, you're tensoring with
Right, so the Schmidt coefficients of this tensor this have to be the same as the Schmidt coefficients of psi. Yeah.
Yeah.
But this is the normal.
Yeah, but this is the this is not this is a Hilbert space norm, not a.
Somehow, you can get or choose two things is when the bases align. Allow you to. So the Schmidt coefficients don't allow you to estimate this one?
Well, I mean, if they did, then the first thing you told us.
Yeah, yeah. The embezzlement holds.
Vern explained it. Using Schmidt coefficients, you cannot do it exactly. But then you can do it up to any epsilon with respect to this node. So some Schmidt coefficients cannot tell you anything about why this sound has. I think it might be a naive argument.
Let me get to the punchline. The punchline is, when the dimension of H is infinite, you can do this exactly in the commuting model. So they're all the same space. And so let me explain a little bit what that means. You see, there's still four wires because there's still 4 spaces. I have to have 4 spaces to talk about psi being an entangled vector. But the UA and the UB, instead of just acting on 2 wires, UA gets to act on 3 because it gets to act on the full resource space, and UB gets to act on 3 because it gets to act on the full resource space, which is the 2 middle wires. But then, of course, UA and UB have to commute. And so we really thought, since we had something finite dimensional that independent of dimension, you couldn't get close on this task, but you could do in the commuting model, that if we stared at it long enough, we'd see a way to contradict Connes out of it. But we couldn't, but I still feel like there might be something in there. So The last two things I want to do, which I'll do after the break, because I want to talk a little bit about quantum to classical XOR games, which turn out to, in a sense, be running embezzlement in reverse. And I want to talk about this newest result that talks about universal embezzlement. So you want to universally be able to do things within epsilon. And there's a theorem that happens if and only if you're in a type 3-1 factor. So I just want to tell you a couple more things that Sam Harris did. And so one of them is we have this BQ22 is not closed, but we know that there's this isomorphism that takes you between that and C star of F get how many outputs is not closed. And that uses that from embezzlement, you know, BQ22 is not closed together with the isomorphisms. And the other thing he did was he defined a family of games so that their Q values and their QC values were the same for all games in this family, if and only if Connes embedding is true. So I want to just give you a glimpse of that without too many details. And the glimpse comes from, if we start with this picture we had, in this picture, we were thinking of, you know, starting here and letting the unitaries act and ending up here. Alternatively, we could be starting here and letting the unitaries act and trying to end up here. And we know if it's the same psi, we can't do that exactly. But this can be phrased in terms of a game. And the idea is the referee gives Alice and Bob a Bell state, and then they're allowed to choose some entangled state, and then they are allowed to act separately on the Bell state, and their goal is to output 0, 0. But of course, what happens if they act, when you read this way, I'm starting with psi epsilon and ending up with psi. So this can't be exactly psi. So when you trace things out for your measurements, you don't get 0, 0 with probability 1, but you solve this game with probability as close to 1 as you want by taking larger and larger spaces where these two vectors are closer and closer together. So that's a quantum to classical game whose value is 1, but there's no finite dimensional strategy that gives you exactly 1. The value is really attained as the soup. And this is kind of, I know I'm not telling you the game exactly, but you can see there's a similar collection of games you could define. And these are called quantum to classical XOR games. And Sam Harris showed that for all games in this family, the quantum and the QC value of the games were equal if and only if Connes embedding is true. So another way to try to find its faults is to try to find a quantum to classical game in his family, that there must be such a game that violates it. Okay, and incidentally, this first game was I think Regev and Vidic were the ones who discussed this Bell state game, or is it someone else? Maybe Laura, in which case I'm embarrassed.
had this remote state preparation with like Debbie and.
Yeah, maybe anyways, if you, well, I'm not good with references, but when you go to the papers, you find the references, and if you get interested in that line, that's there.
Can you play the game a little crazy? Algebra can always say 0, 0. Win.
Yeah, but they have to do a quantum measurement somehow for their output.
But then it's just a POVM whose the 0 outcome is identity. And
Yeah.
so
No. Yeah.
So you're saying there's some more details.
There's details. Yeah.
If you understand the strategy get involved in that, C is part of the strategy, model of the strategy. Right.
Somehow it's restricted strategy.
Yeah,
You're
exactly,
saying
but
your
some-
strategy is restricted.
I think so. Yeah.
Yeah. No, I can't tell you more details, but you get a glimpse of the idea that they're running things this way should be some sort of measurement problem, and that you could maybe make a game out of that. And so the last thing in this topic, the most recent thing, is this work of Lujic, Stottmeister, Reinhard Werner, who many of you probably know, and Wilming. And they wanted to do the following thing. So suppose I have two von Neumann algebras. And again, I'm not going to say everything. In a B of H, which are commuting. And now you'd like to take a unitary and say B of L2 tensor MA. So if you think of our other things, right, an operator here is just like an infinite matrix where each entry comes from M sub A, and it's unitary, only now you have countably many entries. So it's kind of like a UNC infinity element or something. And you'd like a UB with the following property. If for all phi and psi in H unit vectors, there exists a, let me call it gamma. They do this basis free, so they don't have B of L2, but they have, I just like it that way because it's easier to think of these as sort of matrices. For all phi psi and epsilon bigger than 0, there exists a gamma, a UA, and a UB, such that when you do UA, UB, well, UA tensor id, since I'm not drawing wires, so UA acts on 2 of the wires, UB acts on 2 of the wires, and you tensor with the id. Applied to gamma tensor phi, So you think of this as your initial state. This is your shared state, and you'd like to get the shared state back, and you'd like to get the new embezzled state back. Okay, so assume you can do this. And again, I'm leaving out some details, but then MA, MB are type 3-1. So this is what they call universal approximate embezzlement. So
these things very seem to act on one spaces. Because like, I mean, UA tensor identity acts on like L2 tensor H, that's okay. But identity tensor UV acts on, yeah, on H tensor L2 tensor H, or something like that.
yeah, I've
Maybe it should be a UV 1-3 or something.
let me,
So I mean, the whole thing should act on L2 tensor H tensor H or something.
I think we often kind of, if the confusion is about that, we often think that you permute the tensor spaces just so it
works.
the right way, because otherwise it's very hard to, it becomes very hard to write.
Okay.
If that is the question.
What's it mean that gamma's in?
Okay, so the big space is okay. It's like L2 tensor H tensor H.
Yes,
Okay.
and
And then
that's
just
where the
write them the
yes,
way
yeah.
the only way it works. Okay. I see.
yeah, I picked things.
But I don't think that's.
Should gamma be in B of L2 or should it be?
I picked things wrongly somehow. What have I done? They write it so that the individual entries give you, but this doesn't make a lot of sense. Let me quit here. There's some statement of universal embezzlement that if you can approximately universally embezzle for all vectors in the underlying spaces, then you had to be type 3-1.
Universal embezzlement says that I can embezzle any state out while maintaining.
While maintaining
While maintaining my embezzling state, and I'm like in epsilon distance, right? That's the idea.
yeah. And that's so yeah. So whatever the correct idea is here for stating embezzlement this way, if
Can you do it if you have type 3-1? Or?
yes, can do if and only if MA and MB are type 3-1. And there's just there's a hazy cloud that's descended here.
We will have 2 hours here in the last week.
Yeah.
We could ask them.
So it's only approximate, right? It's only
It's approximate, yeah. And that's why they call it embezzlement.
But the states that they want to embezzle, they are finite dimensional, or the state I want to get out, like the analog of EPR pair.
I think they want to use finite dimensions, so the best thing is
Yeah,
but
but
the one that they want.
okay. So that's the
They want to do what we were doing in finite dimensions, but where the input, Alice's input space is infinite dimensional and Bob's input space is infinite dimensional. I clearly have messed up the notation, and it's not going to do any good to us for me to stand here. The paper's on the archive, but all I probably should have said is that there's a connection between type 3-1 and universal approximate embezzlement, and just not tried to write down what was meant by that. But that's the way they state their theorem, is you can do universal approximate embezzlement in the von Neumann algebra setting if and only if the von Neumann algebra is type 3-1. And I shouldn't have tried to write down what those words meant.
But this is like, you say, oh, it's the same as what we show, but for, like, meaning you and Lee and Vern.
The other Vern, yeah.
Like, isn't that like where you embezzle exactly EPR pair? And it's, no? And it's exactly.
Well, we show you can exactly embezzle anything. I mean, that's why I don't like to use the word embezzle. But in the paper with CLeve and L.Liu, we show that you can get anything in the commuting model. You can embezzle,
Okay,
but the resource space has to be infinite dimensional.
Yes.
But we allow a resource space to be infinite dimensional, but we're demanding that our Alice's private space and Bob's private space be finite dimensional in the CLeve, L.Liu, Paulsen stuff. So.
But when you say Alice's private space, Alice now has two spaces, right? The shared resource space?
Well, that's why. So you have HA, a resource space which is not in a bipartite, and HB.
Okay.
And so at the ends, what you're getting here is something entangled, but it's finite dimensional entanglement because these two spaces are finite dimensional, but this space is infinite dimensional.
But so the way I always thought of that result is that you get an EPR pair.
We get anything out.
It follows from this EPR, or that's a different result?
Well, what we prove is you can get anything out.
I'm thinking of this construction where you kind of have these infinitely many EPR pairs and infinitely many zeros.
After we prove this, for the particular case of the Bell state, we show what the construction looks like.
Okay. And then
What the C-star algebras look like, and what the Hilbert space looks like, and how to write it as an infinite tensor product. But that's just for that one example. But then in general, we prove you can always do exact embezzlement.
The resource state will depend on the state you want to embezzle, or no?
Right,
It will depend.
right.
But in the universal embezzlement, it doesn't, right?
Their existence.
Oh, okay. The way you wrote it there, it depends.
It's kind of hard to parse their words for where the for alls and the exists are when you look in their paper, because they keep calling this one omega, but in the statement of the theorem they don't say that omega is a particular fixed vector that has been defined earlier in the paper. They just call it omega. So maybe the intention of the statement of the theorem is that this is a given vector that they've described earlier, but they don't describe omega in the statement of the theorem.
Because somehow, let's say if I think back to this Haydon Van Dam result, approximate embezzling, I mean, the dimension of the state matters that I want to embezzle. That will come
Right.
different.
That's this dimension.
Yes, that dimension. But then isn't the state that I'm going to be using the same? It only somehow depends on the dimension that I want to embezzle, but not on the exact state I want to embezzle.
So ours, given this, you define a state on the tensor product, and then you do the GNS. And so the vector is the unit vector for the GNS, but the GNS space varies with whatever state you're defining.
I understand that, but it just seems to me it would be a natural thing to ask, oh, what happens if I want my embezzlement state to be fixed, right? So
Oh,
you're gonna-
that's,
it's like a natural-
that's trivial in some sense in the commuting model, because once this is an infinite dimensional Hilbert space,
Oh, you just tend
you
to
can,
all of them together?
no, you can conjugate by a unitary to move this vector to any other vector in the state.
Okay, right.
And then if you conjugate the two unitaries by the same unitary, they'll still commute.
Yes, okay, but then in a sense, like. you
So,
don't
so in
have
a
to have
sense, in
the
ours,
full
you
stack.
could fix
Yes,
the,
you can fix the state, and then just the unitaries. I think that's
and then the
much,
unitaries vary, yeah.
I think that's a nicer statement,
Well,
like a strong statement. Because I say, oh, from this fixed resource state, I can embezzle anything.
yeah, but it's just the trivial fact that the unitary group acts transitively on the unit
Yeah, it follows
vectors.
very easily from the result.
I was looking at the, oh no, it is 10:59, sorry. So technically, I have another half hour. If people would like, this bisynchronous has come up a couple of times. I could tell you a little bit about that, because I think there's interesting stuff there that's related to everything else as well, and it relates to the quantum. So is that okay if I? Okay. Good. So I can cover this up. I forgot I'm being recorded. That's really embarrassing.
What do they do with the recording?
Post them on the website. I mean, I'm sure you can ask. It's not to be posted.
So suppose you have one of these P, A, B, X, Ys, the quantum correlations. I don't want to specify which correlation set it's in yet, but I want the inputs and the outputs for both Alice and Bob to all be the same thing. And let's just say it's n elements. So I'm got, n correlation. There's n choices for x, n for y, n for a, n for b. Okay. And so remember, this is synchronous if and only if x equals y implies p, a, b, x, y equals 0 for all a not equal to b. And then the theorem is that with this condition, these come from traces on C-star algebras. Then this and I like to write my PVMs as, for each x, I've got a projection EXA, and as I sum on A, these are 1. And so, if it's in, so say P is in C, Q, C, N, and is synchronous if and only if there's a trace on a C-star algebra and it can be written that way.
So sort of the key idea is that synchronous means that I don't have two sets of here, there, here, there.
Well, in the definition, you have 2 sets. But then you show, what you show is that EXA applied to the state vector has to be the same as that Alice's measurement operator applied to the state vector has to be the same as Bob's. And then when you want to do products, you can just replace this one by Alice's, and then you prove that on this algebra, this state vector defines a trace. And that was what was done in this paper with Yvonne and Winter, Stalky, a lot of people. But so the intuition behind synchronous, of course, is that this is mimicking functions in some sense. Because when you have the same x, you should get the same output. And so you want your densities to never, when you have the same x, you want them to never give different outputs. Probability they give different outputs is 0. Bisynchronous is imitating one-to-one functions. So bisynchronous plus the condition that that if x is not equal to y, so if you evaluate the function at 2 different points, you never get the same output. So that's like a one-to-one function. And then the characterization is that so we use an upper B for bisynchronous. If and only if you have there's a tracial C-star algebra. The EXAs, when you sum on A, of course, have to add to 1, but the new condition is that when you sum on X, they have to add to 1. So it's a it's a representation of the quantum permutation group.
Sorry, already in the synchronous case, these EAK were PVMs.
Yeah, I'm always doing PVMs instead of P. Yeah. And so the question we don't know the answer to, and it's not what I want to do, but I do want someone to answer it for me, is if you take the quantum bisynchronous and close it up, well, that's contained in the QA bisynchronous, but we don't know if it's equal. And there's, so here, this would be a finite dimensional C-star algebra or a matrix algebra. And this is related to various questions. There are some things that would imply this. Like if any time you had EXAs in a finite dimensional matrix algebra, which summed to 1 along rows and summed nearly to 1 along columns, where nearly means in the trace norm, then is there some way to do a dilation and a permutation to get something that sums exactly to 1? But what I'd like to show you is that these turn out to be tied to Claire Anantharama de la Roche's idea of factorizable maps. And they turn out to be tied to your orbital algebras. So the idea is, suppose we're given a P, A, B.
The question that you have for synchronous is true, right?
Yes, if we just put synchronous, it's true. And that was, that held me up for a long time. It was finally Chris Schaffhauser who, using the theory of amenable traces, we were able to prove the synchronous case is true. But it was hard. So maybe there's something about amenable traces on the quantum permutation group that solves this for us. I don't know, but we couldn't see it that way. But we don't know much about quantum permutation groups. But here's the neat little thing we did. So suppose this is a bisynchronous on n elements. Then you look at, I want to define a map using P, which goes from the n by n matrices to the n by n matrices. And you know, X, Y, A, and B are all numbered from 1 to n because they're all the same set. So what I want to do is I want to take the matrix unit. So if you like, you know, bra X, cat Y. And I want to send it to the sum over A and B and the theorem is this is, I can't remember if it's unital or not. Yeah, I think it's unital and trace preserving. And it's CP, so it's a unital quantum channel. And it's factorizable in the sense of de la Roche Antharaman. And so why is that? Well, if you take the, I'll show you in just a moment, yeah. So let me show you the factorizable, and then you'll also know what it means. So if I take my A tau, I have a natural inclusion which just sends a matrix to its value tensored with the identity. And now I have this EXA, but because it's a quantum permutation, it's a unitary. So, right? And so you now look at the map that's conjugation by that unitary. And now you trace out A. And so that's what factorizable is. This is a bit more than factorizable, because factorizable, you don't have to have a unitary here. What you have is you have this canonical way of embedding Mn, and then the adjoint of this gives you another way to embed Mn. And so what you do is you do this canonical, and because Mn is, you can always project onto Mn because it's injective. So you take Mn, you embed it in here in a different way, and then you do the projection of MNA onto Mn. And so factorizable are the ones that you have a star monomorphism into and the adjoint of a star monomorphism. So you don't have this thing in the middle, you just have an MNA, something here, and it's the adjoint. And this is phi p. And so that's one thing. The other thing that's neat is if you look at the fixed points, so you have a C-star algebra with a trace, but you have a magic unitary over the C-star algebra. The EXAs are coming from A. So if you wanted to do universal, you could just put the quantum permutation C-star algebra here.
Is the trace finite, or?
Yeah, it's everything is unital and trace of 1 is 1. So these are special examples of and the other neat thing that comes up is the fixed points of this map phi p. And anytime you just take a bisynchronous is a Frobenius algebra. It's a C-star subalgebra that's also closed under Schur product. And so these, and then if you take a P, which gives a perfect strategy for a graph isomorphism, then you're getting the orbital algebra. So what else did I want to say here? Oh, and the other thing that's neat is I didn't specify where this comes from, but if it comes from Q, then that's when you can factor through, you can take A to be a matrix algebra, and you have factorizable maps that use finite dimensions. When you take it to be QA, then that's when your A you can take to be R omega, and you're looking at things which factorized with R omega as the auxiliary von Neumann algebra. But when you do QC, you just have a generic quantum representation of the quantum permutation group. So I think there's some interesting things here, and it's, we'd just like people to know about this, because leads to nice ways to give factorizable maps. Factorizable maps where, so for example, if you have something that you know is in QC but not in Q, then that gives you a factorizable map where the A you use here and Magdalene and Musat and Roordamp's work, that's what they call the auxiliary von Neumann algebra. So it gives you cases where you need infinite dimensions for your auxiliary von Neumann algebra if you know you're in QC but not Q. And so you can build such examples by, you know, we know now lots of examples of things that are in Q but not QC. QA but not QC is much, much harder, but we know they exist. We don't know if the bisynchronous exist.
This question gets translated here.
Yeah, you can think of it as because each one of these you can think of as a phi p. It's just if every one of these phi p's is approximable by phi p sub j's, which come with a finite dimensional. But I don't know if that's any more useful than. Yeah.
Kind of ask something on the question there with the approximation property. So QA plus or bisynchronous, they will be realizable with the minimal traces on the quantum permutation group. So one of the kind of equivalent or maybe definition even of a minimal trace, you have a recipe maps from approximate factorization of the trace, right? For matrix algebras. So you can take your generators EXA and put it recipe map in a matrix algebra. That will be some finite thing, right? So it will be magic square. So it seems to me like this question is related to this non-dilatability of magic squares to quantum permutations, right? Because when you pass it through a UCP map, you'll just get a magic unitary, magic square.
In magic square where you
Magic
have
square.
POVMs.
Exactly, only POVMs
Instead
that
of
are on the
PVMs.
columns, exactly. And you know that exists by a result of
Yeah, we also had. Yeah, we also had an example of that.
that's the scholars and one more. They are not always delectable to current permutation, so it looks like it's kind of
Saying it might be false.
well, I don't know, but I mean it's kind of it's some flavor of relation to that exactly. Right?
Yeah.
But if let's put it that way, if you were able to delete any magic square, then you would be able to never get them.
Yeah, in fact, we had an example of a doubly stochastic that didn't dilate. But we didn't get the full story there the way they did. We just had an example. We're trying to build a theory, and they did everything very beautiful. Anyway, that's all I wanted to say.